One of the biggest questions in science sounds surprisingly simple. What was before the Big Bang? At first, it feels like there should be an obvious answer. Everything has a beginning. Every person has parents. Every tree grows from a seed. Every star forms from a cloud of gas. So why should the universe be any different? The problem is that the universe doesn't always follow the rules we're used to. In fact, when we look far enough back in time, some of our most basic ideas about space, time, and even the word before start to break down. That doesn't mean scientists have no idea what happened. Far from it. Over the last 100 years, we've learned an incredible amount about the history of the universe. We've discovered that the universe is expanding. We've measured light that's been traveling through space for almost 14 billion years. We've recreated some of the conditions that existed just fractions of a second after the Big Bang inside particle accelerators. Thanks to all of this, scientists can reconstruct much of the universe's early history with surprising accuracy. But there's a catch. The farther back we go, the less certain things become. Eventually, we reach a point where our best theories stop giving reliable answers. That's where today's journey begins. In this documentary, we'll go all the way back to the earliest moment that modern physics can describe. We'll look at the evidence for the Big Bang, explore what happened during the universe's first moments, and then examine the biggest ideas scientists have proposed about what came before. Some of those ideas are backed by strong evidence. Others are still mathematical possibilities. We'll make it clear which is which. Because in science, there's an important difference between something that's well supported and something that's simply an interesting idea. So before we ask what came before the Big Bang, let's first answer a much more important question. What exactly was the Big Bang? If you ask people what the Big Bang was, you'll probably get a lot of different answers. Some imagine a giant explosion. Others picture a tiny ball of matter suddenly appearing out of nowhere. Some think it happened at a specific point in space, almost like a bomb going off. The problem is that none of those pictures is quite right. The Big Bang wasn't an explosion in space. It was the expansion of space itself. That might sound like a small difference, but it's one of the most important ideas in modern cosmology. Here's a simple way to think about it. Imagine drawing a few dots on the surface of a balloon. Each dot represents a galaxy. Now start inflating the balloon. As the balloon expands, every dot moves farther away from every other dot. The dots aren't moving across the rubber. The rubber itself is stretching. That's similar to what happens in our universe. On the largest scales, galaxies aren't racing through empty space because of some giant explosion. Instead, the space between them is expanding. Of course, this analogy isn't perfect. The balloon has a center. The universe doesn't appear to. The balloon expands into the air around it. As far as we know, the universe isn't expanding into anything. The analogy is only meant to show that space itself can expand. That leads to another interesting question. If every galaxy appears to be moving away from us, does that mean we're at the center of the universe? Actually, no. Imagine you lived on a different galaxy billions of light years away. You would see the same thing. Other galaxies would appear to be moving away from you as well. Every observer sees the expansion in much the same way. That's one reason scientists don't think the universe has a special center. So how do we know the universe is expanding in the first place? The answer comes from light. Every chemical element leaves a unique pattern in the light it produces. You can think of it as a fingerprint. Hydrogen has one fingerprint. Helium has another. Iron has another. When astronomers looked at the light coming from distant galaxies, they noticed something strange. Those fingerprints had shifted. Almost every distant galaxy showed the same pattern. Its light had moved toward the red end of the spectrum. This effect is called redshift. The farther away a galaxy was, the greater its redshift. In other words, the farther away a galaxy is, the faster it's moving away from us. This relationship is known as Hubble's law, and it was one of the first major clues that the universe is expanding. There's another analogy that helps here. Imagine raisins inside a loaf of bread. As the dough rises in the oven, Every raisin moves farther away from every other raisin. The raisins themselves aren't expanding. The dough is. Galaxies behave in a similar way. They're being carried apart because the space between them is growing. This doesn't mean everything in the universe is expanding. The Earth isn't getting bigger. Neither is the solar system. The Milky Way isn't being pulled apart by cosmic expansion either. That's because gravity is much stronger than the expansion of space on relatively small scales. Expansion only becomes noticeable across the enormous distances between groups of galaxies. Now let's rewind the clock. If the universe is expanding today, then in the past it must have been smaller. Go back far enough, and galaxies get closer together. Temperatures rise. Matter becomes denser. Eventually, we reach an incredibly hot, dense state that existed about 13.8 billion years ago. This is what cosmologists call the hot Big Bang. Notice what we didn't say. We didn't say that all the matter in the universe was squeezed into a tiny ball floating in empty space. That's a common misconception. The early universe wasn't a tiny object sitting inside a much larger empty universe. Space itself was much smaller than it is today. Finally, there's one question almost everyone asks. Where did the Big Bang happen? The surprising answer is everywhere. Not because an explosion spread across the universe, but because every part of today's observable universe was once part of that hot, dense early state. The place where you're sitting right now was part of the Big Bang. So was every galaxy we can see. There isn't a single point in space where it happened. The Big Bang happened everywhere because space itself was expanding everywhere. So far, we've talked about the Big Bang as a scientific model. But how do we know it's actually correct? In the next chapter, we'll look at the evidence. And as you'll see, it's not based on one discovery. It's based on several completely independent observations that all point to the same conclusion. So far, we've talked about the Big Bang as if it were a fact. But in science, that's never enough. The real question is, what's the evidence? Scientists don't accept ideas because they sound reasonable. They accept them because observations support them. In the case of the Big Bang, there isn't just one piece of evidence. There are several, and they were discovered independently over many decades. What's remarkable is that they all tell the same story. Let's start with the first one, the expanding universe. In the previous chapter, we saw that distant galaxies are moving away from us. The farther away they are, the faster they appear to recede. This is exactly what we'd expect if space itself is expanding. But expansion alone doesn't prove the Big Bang. It only tells us that the universe was smaller in the past. To understand what that means, scientists looked for more evidence. And they found it. The oldest light in the universe. If the early universe was extremely hot, then it should have been filled with intense radiation. As the universe expanded and cooled, that radiation would lose energy and become much colder. It shouldn't disappear. It should still be here today, just much weaker. 4 years, this was only a prediction. Then, in 1965, 2 radio astronomers accidentally found it. No matter where they pointed their antenna, they detected the same faint microwave signal. At first, they thought something was wrong with their equipment. They checked everything. They even cleaned bird droppings out of the antenna. The signal didn't go away. What they had discovered was the cosmic microwave background, often called the CMB. It's the oldest light we can observe. It has been traveling through space for about 13.8 billion years. In a sense, it's a snapshot of the universe when it was only about 380,000 years old. That may sound old, but on cosmic timescales, it's surprisingly early. Before that time, the universe was so hot that light couldn't travel freely. It was constantly scattered by charged particles. Only after the universe cooled enough for atoms to form could light move across space. That ancient light is still reaching us today. Tiny differences that changed everything. At first glance, the cosmic microwave background looks almost perfectly uniform. Its temperature is nearly the same in every direction. But when satellites measured it more precisely, they found tiny variations. They're incredibly small, only about 1 part in 100,000. Those tiny differences mattered. Regions that were slightly denser contained a little more gravity. Over billions of years, gravity pulled more matter into those regions. Eventually, they became galaxies, stars, and planets. Without those tiny fluctuations, the universe would be very different. There would likely be no galaxies, no stars, and no life as we know it. The elements tell the same story. There's another test of the Big Bang, and it comes from chemistry. The early universe was hot enough for nuclear reactions to take place. For a few minutes, conditions were just right to produce the lightest elements: hydrogen, helium, and tiny amounts of lithium. As the universe continued expanding, it cooled too quickly for those reactions to continue. That means the Big Bang makes a very specific prediction. It predicts how much hydrogen and helium should exist today. When astronomers measure the oldest gas clouds in the universe, the numbers match those predictions remarkably well. That's an important result. It means the same model that explains the expansion of the universe also correctly predicts its chemical composition. Why this matters? Any one of these discoveries would have been impressive on its own. But that's not what convinced scientists. What makes the Big Bang model so powerful is that completely different observations all point to the same picture: the expansion of the universe, the cosmic microwave background, the abundance of the light elements. Each was discovered independently. Each measures something different, yet they all tell the same story. That's exactly what scientists hope to see. Not one experiment supporting an idea. Many independent observations reaching the same conclusion. Does that mean the Big Bang model explains everything? Not even close. In fact, once scientists accepted it, they immediately ran into new questions. Some of them were so serious that they seemed to suggest the model was incomplete. And solving those problems would lead to one of the biggest breakthroughs in modern cosmology: the idea known as cosmic inflation. Now that we know the Big Bang model is supported by strong evidence, let's rewind the clock. Not millions of years, not thousands, not even 1 second. Let's go all the way back to the earliest moments that modern physics can describe. The closer we get to the beginning, the more extreme the universe becomes. Temperatures rise. Matter becomes denser. The laws of physics start behaving in ways we never experience in everyday life. At first, our theories work remarkably well. But eventually, we hit a wall. Let's see how we get there. The first second. By the time the universe was 1 second old, it was already enormous compared to the scales of particle physics. It was still incredibly hot, around 10 billion degrees. At those temperatures, atoms couldn't exist. Even atomic nuclei struggled to survive. Instead, the universe was filled with a dense mixture of particles and radiation. As it expanded, it cooled. That cooling allowed new structures to form. Within the first few minutes, protons and neutrons combined to create the first atomic nuclei, mostly hydrogen and helium. The atoms themselves wouldn't appear until much later, about 380,000 years after the Big Bang. Going even further back. Now let's go back even farther. 1,000th of a second, 1,000,000th, 1,000,000,000th. The farther back we go, the higher the energy becomes. Eventually, matter no longer behaves the way we're used to. The 4 fundamental forces of nature also begin to look very different. Today, they're separate: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. But many physicists think that at extremely high energies, some of these forces were once united. As the universe cooled, they separated into the forces we see today. Exactly how this happened is still an active area of research. The Planck Epoch. Eventually, we reach a moment called the Planck Epoch. This lasted only until about 10⁻⁻43 seconds after the Big Bang. That's a decimal point followed by 42 zeros before you reach the number 1. It's such a tiny fraction of a second that it's almost impossible to imagine. And yet, it's one of the most important moments in the history of the universe. Here's the problem. Our 2 best theories disagree about what happened there. On one hand, we have general relativity. It does an excellent job describing gravity and the large-scale structure of the universe. On the other hand, we have quantum mechanics. It explains how nature behaves at the smallest scales. Both theories have been tested countless times. Both work incredibly well. But under the extreme conditions of the Planck Epoch, they can't both be right in their current form. Each predicts things the other cannot fully explain. In other words, our mathematics breaks down. It's important to understand what that means. It doesn't mean the universe stopped existing. It doesn't mean something magical happened. It simply means our current theories are no longer good enough to describe those conditions. This is the first major limit of modern cosmology. Not because we can't build a better telescope, but because we don't yet have a theory that successfully combines gravity with quantum mechanics. Physicists call this missing theory quantum gravity. Finding it is one of the biggest goals in modern physics. A timeline we can trust. So where does that leave us? From today back to about 1 second after the Big Bang, our understanding is extremely strong. Go back to the first few minutes, and we're still on solid ground. Even earlier, many parts of our models continue to match observations remarkably well. But once we approach the Planck Epoch, confidence drops sharply. That's the point where evidence gives way to educated guesses. And it's also where many of the ideas we'll discuss later begin. Some try to replace the singularity with a bounce. Others suggest the universe existed before the Big Bang. Others argue that time itself began here. The truth is, we don't know. And that's exactly why this part of cosmology is so exciting. But before we explore those ideas, we need to understand another breakthrough. One that solved several major problems with the original Big Bang model. It's called cosmic inflation. And without it, the universe we see today would be much harder to explain. By the late 1970s, the Big Bang model had become incredibly successful. It explained why the universe is expanding. It correctly predicted the cosmic microwave background. It even got the abundance of the light elements right. But there was a problem. Actually, there were several. The Big Bang model described the universe very well. It just didn't explain why the universe looked the way it does. That's where inflation comes in. Problem 1. Why is the universe so uniform? Take a look at the cosmic microwave background. No matter which direction we look, its temperature is almost exactly the same. The differences are tiny, only about 1 part in 100,000. At first, that sounds perfectly normal. But it's actually a puzzle. Here's why. Light travels at a finite speed. That means 2 regions on opposite sides of the observable universe have never had enough time to exchange information. As far as the standard Big Bang model is concerned, they were never in contact. So why do they have almost exactly the same temperature? It's a bit like finding 2 ovens on opposite sides of a city, both set to exactly the same temperature, even though they've never been connected. You'd probably wonder if they shared a common history. Scientists wondered the same thing about the universe. This is known as the horizon problem. Problem 2. Why is space so flat? The next puzzle is geometry. On very large scales, the universe appears to be remarkably flat. That doesn't mean it's two-dimensional like a sheet of paper. It means the geometry of space is very close to what's called Euclidean geometry. Parallel lines stay parallel. The angles of a large triangle add up to almost exactly 180 degrees. Measurements show that the universe is astonishingly close to this kind of geometry. The question is, why? Even a tiny deviation in the early universe would have grown over time. Yet today, space is still extremely close to flat. This is called the flatness problem, a simple idea with huge consequences. In 1980, physicist Alan Guth proposed a possible solution. What if, very early in its history, the universe went through a brief period of incredibly rapid expansion? Not just fast, unimaginably fast. In a tiny fraction of a second, the universe could have expanded by an enormous factor, much faster than during the rest of cosmic history. This idea became known as cosmic inflation. The key point is that inflation happened before the hot Big Bang phase we're most familiar with. If inflation occurred, It would have stretched space so dramatically that regions once close together ended up billions of light years apart. That means those distant regions could have shared the same temperature before inflation pulled them apart. In other words, inflation offers a natural explanation for the horizon problem. Why inflation makes space look flat? There's another consequence. Imagine standing on Earth. From where you are, the ground looks flat. Of course, we know Earth is a sphere. It only looks flat because we're seeing a tiny part of its surface. Now imagine making Earth larger and larger. The bigger it gets, the flatter that small patch appears. Inflation works in a similar way. If space expanded enough, any large-scale curvature would become incredibly difficult to detect. That's why the universe appears so close to flat today. Inflation doesn't prove space is perfectly flat. It explains why it would look that way. Did inflation really happen? At this point, it's important to be careful. Inflation is one of the leading ideas in modern cosmology. It explains several puzzles with a single mechanism, and many of its predictions match what astronomers observe. But that doesn't mean inflation has been proven. There isn't just one version of inflation. There are many models, each making slightly different predictions. Some have survived observational tests better than others. Others have already been ruled out. That's exactly how science works. Ideas make predictions. Observations test them. The models that fail are discarded. The ones that survive remain under consideration. Today, many cosmologists think some form of inflation probably occurred. But the details are still being worked out. Tiny quantum fluctuations. Inflation may also explain something even more remarkable. Remember those tiny temperature differences in the cosmic microwave background? According to many inflation models, they began as microscopic quantum fluctuations, random variations at the smallest possible scales. Inflation stretched those tiny fluctuations across the entire universe. Over billions of years, gravity amplified them. They eventually became galaxies, stars, planets, and everything else we see today. If that's correct, then every galaxy in the night sky, including our own, can trace its origin back to tiny quantum fluctuations in the very early universe. It's one of the most fascinating ideas in modern physics. But once again, it's an idea supported by evidence, not a proven fact. The next question. Inflation solves several important problems, but it also creates new ones. What caused inflation to begin? Why did it stop? And could it still be happening somewhere else? Those questions lead directly to the next chapter. Because one possible answer suggests that asking what happened before the Big Bang may not make sense at all. We've come a long way. We know the universe is expanding. We know the Big Bang model is supported by multiple lines of evidence. And we've seen why many cosmologists think inflation probably happened. Now we're ready to ask the question that brought us here. What happened before the Big Bang? The first answer might be the strangest one. Maybe nothing happened before it. Not because the universe appeared out of nowhere, but because there may not have been a before at all. Why before might be the wrong question. Think about how we use the word before. Breakfast happens before lunch. Monday comes before Tuesday. Cause comes before effect. The word only makes sense if time already exists. Now imagine asking, what's north of the North Pole? At first, it sounds like a perfectly reasonable question. But the closer you think about it, the stranger it becomes. The North Pole is the northernmost point on Earth. Once you're there, there is no direction that's farther north. The question isn't difficult. It's based on an incorrect assumption. Some physicists think the same could be true for the Big Bang. If time itself began there, then asking what happened before it may be like asking what's north of the North Pole. The question assumes something that may not exist. What does general relativity say? This idea comes from Einstein's theory of general relativity. If we use its equations to describe the expanding universe and run time backward, everything gets smaller, hotter, and denser. Eventually, the equations reach a point where density and temperature become infinite. This is what's known as a singularity. It's often described as the beginning of the universe. But that's a simplification. A singularity doesn't necessarily mean nature contains infinities. More often, it tells physicists that a theory has reached its limit. In other words, general relativity stops giving reliable answers. That's an important distinction. The equations predict a singularity. Whether one actually existed is something we don't know. So, did time begin? Here's the honest answer. We don't know. General relativity suggests that space and time are deeply connected. If space had a beginning, time may have as well. But general relativity is incomplete. It doesn't include quantum mechanics. And we already know that both theories are needed to describe the earliest moments of the universe. Until physicists develop a successful theory of quantum gravity, we can't say with confidence what happened at, or before, the Big Bang. What scientists actually mean. This is where a lot of confusion comes from. You'll often hear statements like, "There was no time before the Big Bang." That's a useful shortcut, but it's not something we've proven. A more accurate way to say it is this. According to our current understanding of general relativity, time may have begun with the Big Bang. If that's correct, then the question, what happened before, may not have a physical meaning. That's a subtle difference. But in science, small differences in wording matter. Is that the end of the story? Not even close. General relativity gives us one possible answer. But many physicists think the story doesn't end there. Some believe the singularity never existed. Others think the universe went through an earlier phase before the Big Bang. Some even suggest that our universe is just one chapter in a much longer cosmic history. These ideas come from attempts to combine gravity with quantum mechanics. None has been confirmed, but all of them are active areas of research, and they lead us to one of the most interesting possibilities in modern cosmology. What if the Big Bang wasn't the beginning of everything, but the result of something that came before? That's the idea behind the Big Bounce. If general relativity is right, then the universe began with the Big Bang. But as we saw in the previous chapter, general relativity isn't the whole story. It doesn't include quantum mechanics. And that's a problem, because the earliest moments of the universe were both incredibly massive and incredibly small. That's exactly where both theories should matter. So what happens if we include quantum physics? No one knows for sure. But some models predict something surprising. Instead of a beginning, the Big Bang may have been a bounce. Why scientists came up with this idea? The Big Bounce wasn't invented just to answer the question, what came before the Big Bang? It came from a different problem. The singularity. According to general relativity, if we keep running the universe backward, density eventually becomes infinite. Temperature becomes infinite. The equations stop making sense. Whenever physicists see infinities like that, they become suspicious. History has shown that infinities often mean a theory has reached its limits. Not that nature literally contains infinite values. Many physicists think that's exactly what's happening here. The singularity may not be a real object. It may simply mark the point where general relativity no longer works on its own, where quantum physics changes the picture. Several approaches to quantum gravity suggest that space itself may have a smallest possible scale. If that's true, then the universe can't be compressed forever. Eventually, quantum effects become so strong that they change how gravity behaves. Instead of continuing to pull everything inward, gravity may effectively become repulsive under these extreme conditions. The collapse would slow down, then stop, then reverse. Instead of ending in a singularity, the universe would begin expanding again. That's the basic idea behind the Big Bounce. A simple analogy. Imagine dropping a rubber ball onto the floor. As it falls, gravity speeds it up. When it hits the ground, the ball compresses. For a brief moment, it stores energy. Then it bounces back. The Big Bounce is similar in one important way. A collapsing universe doesn't end in a singularity. It rebounds into a new phase of expansion. Of course, the analogy isn't perfect. The universe isn't bouncing off a surface, and it isn't moving through space. Space itself is what's contracting and expanding. The analogy is only meant to illustrate the idea of a rebound instead of an ending. Loop quantum cosmology. One of the best-known versions of the Big Bounce comes from loop quantum cosmology. It's based on a broader framework called loop quantum gravity, which tries to combine general relativity with quantum mechanics. In this model, space isn't perfectly smooth. Instead, it has an underlying quantum structure. You can think of it like a digital photo. From far away, the image looks perfectly smooth. Zoom in far enough, and you start seeing individual pixels. The picture isn't actually continuous. It's made of tiny building blocks. Some physicists think space-time could work in a similar way. If that's true, the equations no longer produce an infinite density singularity. Instead, they predict a minimum possible size for the universe. After reaching that minimum, expansion begins again. Is there any evidence? This is the most important question. Right now, no observation shows that our universe went through a previous contraction. Scientists have looked for possible clues. Some models predict subtle patterns in the cosmic microwave background. Others suggest specific gravitational wave signals. So far, none of these predictions has been confirmed. That doesn't mean the Big Bounce is wrong. It simply means we don't have evidence for it yet. What does this mean? The Big Bounce is an interesting possibility because it removes the singularity. Instead of saying the universe began from a point where physics breaks down, it replaces that point with new physics. It's also one of the few ideas that naturally allows for a universe before our own. But it's still a hypothesis. It depends on a theory of quantum gravity that hasn't yet been confirmed by experiments. So while it's taken seriously by many physicists, it isn't part of the standard model of cosmology. It's one possible answer, not the answer. But the Big Bounce raises another question. If one universe can give rise to another, could this process happen over and over again? Or even produce many universes at once? That idea brings us to one of the most debated topics in modern cosmology: the multiverse. The Big Bounce suggests there may have been a universe before ours. But there's another idea that's even more surprising. What if new universes are still being created today? Not inside our universe, but as part of a much larger reality. This idea comes from something we've already talked about: cosmic inflation. Inflation may not end everywhere. Earlier, we explained inflation as a brief period of extremely rapid expansion in the early universe. In the simplest version, inflation begins, lasts for a tiny fraction of a second, and then ends. The hot Big Bang follows. But when physicists studied inflation in more detail, they found something interesting. In many models, inflation doesn't have to end everywhere at the same time. It can stop in one region while continuing in another. Where inflation ends, a hot Big Bang begins. Matter forms. Stars and galaxies eventually appear. Meanwhile, somewhere else, inflation keeps going. And as it continues, more regions stop inflating and form their own universes. If this process never completely ends, it's called eternal inflation. Bubble universes. A common way to picture this is with bubbles. Imagine water starting to boil. Bubbles form in different places. Each grows on its own. Now replace the water with inflating space. Each bubble represents a universe where inflation has ended. Inside that bubble, everything follows the familiar story. The universe expands. Stars form. Galaxies appear. Outside the bubble, inflation continues. Eventually, more bubbles form. Each becomes its own universe. The analogy isn't perfect. These bubbles aren't floating through ordinary space. Space itself is part of the process. The analogy just helps us picture how many separate universes could form. Does inflation automatically mean a multiverse? This is a good place to clear up a common misunderstanding. Inflation and the multiverse are not the same thing. The evidence for inflation is much stronger than the evidence for a multiverse. In fact, some models of inflation don't predict a multiverse at all. The multiverse appears only in certain versions of inflation. That's an important distinction. Could other universes have different laws? Some multiverse models suggest that different universes might not be identical. The basic laws of physics could stay the same, while some of the constants are different. For example, gravity might be stronger or weaker. The universe might expand much faster or collapse before stars have time to form. In many of those universes, complex structures might never appear. No stars, no planets, possibly no life. That leads to an interesting idea called the anthropic principle. The basic argument is simple. If many different universes exist, we shouldn't be surprised to find ourselves in one that's capable of supporting life. After all, observers can only exist in a universe where observers are possible. Some physicists find this idea useful. Others think it explains too little because it's difficult to test. The debate is still ongoing. Can we detect another universe? This is the obvious question. If other universes exist, can we ever find them? Maybe. Some physicists have suggested that if two bubble universes collided in the distant past, they might have left faint patterns in the cosmic microwave background. Others hope future observations of gravitational waves could reveal evidence for the kind of inflation that produces a multiverse. So far, none of these searches has found convincing evidence. Right now, there is no direct observational proof that other universes exist. So where does that leave us? The multiverse is one of the most fascinating ideas in modern cosmology. It's based on serious mathematics. It's discussed by serious physicists, but it hasn't been confirmed. At the moment, it's best thought of as a possible consequence of some inflation models, not an established fact about reality. That distinction is important. Science moves forward by testing ideas, not by assuming they're true because they sound exciting. But the multiverse isn't the only alternative to a universe with a beginning. Some physicists have proposed something different. Instead of many universes existing at the same time, what if the same universe keeps coming back over and over again? That brings us to the idea of a cyclic universe. So far, we've looked at two very different ideas. The Big Bounce suggests our universe may have been preceded by another one. The multiverse suggests many universes could exist at the same time. But there's another possibility. What if the universe has no true beginning? Because it never stops. The idea of a cyclic universe. The basic idea is surprisingly simple. Instead of beginning once and existing forever, the universe goes through repeated cycles. One cycle ends. Another begins, then another, and another. In this picture, the Big Bang isn't the beginning of everything. It's simply the beginning of the current cycle. Different versions of this idea work in different ways, but they all share one goal: to explain the Big Bang without treating it as the absolute beginning of reality. Why consider this idea? One reason is the singularity problem. If the Big Bang really began with infinite density, our current theories stop working. Many physicists see that as a sign that something is missing. A cyclic universe offers another possibility. Maybe the Big Bang wasn't the start of everything. Maybe it was the transition from an earlier phase of the universe. The ekpyrotic model. One of the best-known cyclic models is called the ekpyrotic universe. It comes from ideas related to string theory. Now, it's important to be clear. String theory itself hasn't been confirmed, and neither has the ekpyrotic model, but it's still an active area of research. The basic idea goes like this. Some versions of string theory suggest our universe could be part of a much larger, higher-dimensional reality. Instead of existing on its own, our universe might be like a huge surface, often called a brane. If another brane exists nearby, the two could slowly move toward each other. Eventually, they collide. That collision releases an enormous amount of energy. From inside our universe, it could look very much like a Big Bang. In this picture, the Big Bang isn't the beginning of everything. It's the result of a collision. Does this mean the universe is older than 13.8 billion years? Possibly. The observable universe is about 13.8 billion years old. That's well supported by observations. But if one of these cyclic models is correct, the larger reality containing our universe could be much older. maybe billions of years older, maybe infinitely old. Right now, we simply don't know. Roger Penrose's different approach. Not every cyclic model relies on string theory. Physicist Roger Penrose proposed a very different idea called conformal cyclic cosmology, or CCC. Instead of focusing on what happened before the Big Bang, Penrose looked at the incredibly distant future. Over unimaginable lengths of time, stars burn out. Black holes slowly evaporate through Hawking radiation. Eventually, the universe becomes extremely cold and almost completely empty. Penrose noticed something interesting. If the universe eventually contains no massive particles, some of the mathematics begins to look surprisingly similar to the mathematics describing the very early universe. His idea is that the end of one cosmic era could become the beginning of the next. Not through a bounce, not through a collision, but through a mathematical transformation of space-time itself. It's one of the most original ideas in modern cosmology. Is there any evidence? Penrose and his collaborators have argued that they may have found hints of this idea in the cosmic microwave background. Other researchers have looked at the same data. So far, most have concluded that the evidence isn't convincing. That doesn't prove the theory is wrong. It simply means the observations haven't confirmed it. And that's where things stand today. What should we take away? Cyclic models offer an interesting alternative to a universe with a single beginning. Some rely on quantum gravity. Some rely on string theory. Some don't. But they all try to answer the same question. Can the Big Bang be explained without being the absolute beginning of everything? Right now, we don't know. None of these models has enough evidence to replace the standard picture of cosmology. But they continue to inspire new research and new observations. And there's one more idea we still haven't explored. Maybe we're asking the wrong question entirely. Maybe the universe didn't come from a previous universe at all. Maybe it emerged through the laws of quantum physics themselves. To understand that possibility, we first need to answer a surprisingly difficult question. What do physicists actually mean when they say nothing? We've explored several possible answers to the question of what came before the Big Bang. Maybe there was a previous universe. Maybe there are countless universes. Maybe the universe goes through endless cycles. But there's one more possibility. What if the universe didn't come from something else at all? At first, that sounds impossible. After all, we've all heard the phrase, "Nothing comes from nothing." In everyday life, that's true. An empty room doesn't suddenly fill with furniture. A planet doesn't appear out of nowhere. So why would the universe be any different? The answer depends on one surprisingly important question. What do we actually mean by nothing? Nothing in everyday life. When most people hear the word nothing, they imagine complete emptiness. No matter, no energy, no space, no time, absolutely nothing. But in physics, the word is often used differently. Sometimes nothing refers to empty space. The problem is that empty space isn't actually empty. The quantum vacuum. According to quantum mechanics, even the emptiest region of space isn't perfectly still. Fields are always present. Tiny fluctuations constantly appear and disappear. Particles can briefly pop into existence before disappearing again. This doesn't violate the laws of physics. It's a natural consequence of quantum theory. Physicists call this state the quantum vacuum. Despite the name, it isn't nothing in the philosophical sense. It's a physical state with measurable properties. We've even observed effects that depend on these vacuum fluctuations. So this isn't just mathematics. It's part of experimentally tested physics. Could the universe have emerged from a quantum state? Some physicists have asked an obvious question. If quantum processes can produce particles, could similar physics have played a role in the origin of the entire universe? Several models explore this possibility. One of the earliest was proposed by physicist Edward Tryon, who suggested that the universe might be a large-scale quantum fluctuation. Later, physicists such as Alexander Vilenkin developed models in which a universe could emerge through quantum tunneling. These ideas don't describe a universe appearing by magic. They're mathematical models based on quantum mechanics and general relativity. Whether they describe reality is still unknown. What about a universe from nothing? You've probably heard this phrase before. It became widely known through books and public lectures. But it's also one of the most misunderstood ideas in modern physics. In these models, nothing usually doesn't mean the complete absence of everything. It often refers to a state with no classical space or time, but one that's still described by the laws of quantum physics. That's very different from the everyday meaning of the word. This distinction is easy to miss, but it's essential. So, what came before? After everything we've discussed, the honest answer is still the same. We don't know. Maybe time began with the Big Bang. Maybe our universe emerged from an earlier one. Maybe inflation is constantly creating new universes. Maybe quantum gravity will reveal a completely different picture. Right now, the evidence isn't strong enough to choose between these possibilities. And that's not a weakness of science. It's one of its strengths. Science doesn't fill gaps with certainty. It keeps asking questions until better evidence arrives. Final thoughts. At the beginning of this documentary, we asked a simple question. What was before the Big Bang? It turns out that answering it isn't simple at all. The deeper scientists look into the earliest moments of the universe, the more they discover that familiar ideas, like space, time, and even before, may not work the way we expect. Some hypotheses may eventually be confirmed. Others will probably be abandoned. That's how science has always moved forward, not by protecting old ideas, but by replacing them with better ones when the evidence demands it. For now, the Big Bang remains the earliest chapter in the history of the universe that is strongly supported by observations. What happened before that chapter, if before even exists, is still one of the greatest open questions in science. And perhaps that's what makes it so fascinating. Not that we already know the answer, but that we're still learning how to ask the right question.